Hi everyone, today I'll be talking about work and energy. So first of all, what is work? Well, a simple definition is how much exertion was done, right? So the way we define it in physics is quite simple. Work, which I'll represent with a W, is equal to force dotted with the distance the force went through. And I don't think I've talked about the dot product yet. So force and displacement are both vector quantities. There is no natural way to just multiply vector quantities, right? For scalars, you just multiply them. But for vector quantities, we have a special type of multiplication. There are two types of multiplication for vector quantities. One is called the dot product, and the other is called the cross product. I know it looks exactly like this, so sorry about that. But the dot product is defined as, so if I have A dotted with B, it's defined as the magnitude of A, which I'll just call as A, the magnitude of B, which I'll just call as B, and the cosine of the angle between the two of them. So it's a kind of saying, okay, how much of A and B are in the same direction, so as to speak. That's what dot product means. Cross product is entirely the opposite. It's A cross B equals AB sine theta. So it has to do with how perpendicular are A and B to each other. So the more perpendicular they are, then the greater this value AB sine theta would be. All right. Another way to define the dot product is by using components. So if I have A dotted with B, and A, let's say, is a x in the I hat direction, or let me use x hat plus ay in the y hat direction dotted with bx in the x hat direction plus by in the y hat direction. So I broke A and B down into their components. I just substituted A with this whole stuff over here, all right? That's all I'm trying to say. And since it's a two-dimensional problem, let's say, A has two components. If it was 3 dimensions, we'd have another component. Dot product is simple. What we do is we actually just multiply the similar components. So it becomes ax bx plus ay by. And you can actually derive this result by using this ab cosine theta idea. Just multiply the terms out as you usually would in math. And then you would end up with x dotted with x and x dotted with y terms. And you can actually think about, okay, what is x dotted with x? It's x times x cosine of theta, and x is a unit vector, so the magnitude is just 1, and they're in the same direction. So cosine of 0 is 1. But on the other hand, if you have x dotted with y, that's x magnitude of x hat, magnitude of y hat, times the cosine of the angle between x and y, but we know x is this way, y is that way, so they're 90 degrees. Cosine of 90 is 0, so this whole thing goes to 0. So that's why we don't have ax times by or ay times bx ever, because the dot between opposite components or different components, they're perpendicular to each other. All right, so I hope this makes sense. If not, review vectors, understand what dot product is, because I think it's helpful to understand where work comes from. All right, so this is the definition for work. Work is a scalar quantity, but it can be negative. And that really means something. So it doesn't have to do with direction, but it has to do with how is the work being exerted. So let's talk about how to calculate work and what different values of work mean, right? So let's say there's this box, all right? And let's assume that there's no friction for now. And let's say there's a person and they're pushing it. And they're applying 10 newtons of force over a distance of, let's say, 3 meters. So that's continuous 10 newtons over 3 meters. So the work done is F dotted with D. And since F and D are in the same direction, the displacement started from here, ended here. So the direction of displacement is also the same as the direction of force. So it's just 10 times 3 Newton meter, which is 30 Newton meter. So that's positive work. And Newton meter, that unit, we can call it joules. So from now on, Newton meter will be called joules. All right, that's the unit for work or energy in general. So this is 30 joules. So the work done shifted the box from this initial location here to the final position, which is here. All right, so from here to there, and it was in the direction. The force was in the same direction as displacement. That's why the work done is positive. Now what if, let's say this box is already moving, all right? It's already moving, let's say, in this direction. And let's say there's a person that's trying to push this box in the opposite direction. And they are applying a force of, again, let's say 10 newtons. So it's in 10 newtons in this direction. But the box is actually moving very fast, so they're hardly able to push it towards the opposite direction. So what happens is the box starts over here initially, and it ends up here in this final location. So this is the final position. So the displacement is actually in this direction. So you can see that they're in opposite directions. And let's say the displacement was, I don't know, well, let's just choose 3 again, just for fun. So let's say that was 3 meters. So in this case, the work done, it's not a vector quantity, is F dotted with D once again. And here, F is 10. So they're not in the same direction. So either you can say, oh, they're not in the same direction, that means work has to be negative, and you can just multiply these two together and get negative 30, or you can write it down properly, which that's what I'm going to do. So the angle between the force and displacement, you can actually draw these arrows right next to each other, right? These are the 2 arrows, and the angle between them is a whopping 180 degrees. So you have 10 times 30 times cosine of 180 degrees. And if you have a calculator, that's not a nice way to write 0. If you have a calculator, go ahead, put it in, or if you know your tables, it's -1, cosine of 180. So you get negative 30, and the unit is joules, all right? So you can see that when they're in opposite directions, it's negative. Now what if we have this box, and it's moving upward, and you're applying a force on it to try to displace it perpendicularly, but it doesn't move, it doesn't budge. So it's just moving upwards. In this case, so your force, I'll draw the force with blue, let's say it's 10 newtons, and it moves up 30, let's say 3 meters upward, so that's the displacement direction. If there's a 90-degree angle between the 2 of them, then F dotted with D is, again, FD cosine theta, and that's just, the angle theta is 90 degrees, so that becomes 10 times 3, and cosine of 90, if you know your tables right, it's 0, so the answer is 0. So you can see that work done by a force that's perpendicular to the displacement will always be 0, all right? That's a very important point here, and it comes again and again, and a lot of definitions that we have are really rely on this property of them being perpendicular. When the displacement and the force are perpendicular to one another, the total work is 0. This is a very useful property. So that's work. Now we're going to talk about another term called energy. Now work and energy sound pretty much the same, but they aren't. Work is more dynamic. Work can be defined as the change in energy. So E final minus E initial, kind of like that. Energy is a more fluid term. We have different types of energy. You can calculate specific types of energy. So energy has different types. We have potential energy. That's energy stored in something. So it's the potential for it to be dynamic, kind of. That's why it's like potential energy. It has potential, but it hasn't done anything yet. And the 2 very popular forms of potential energy are the gravitational potential energy, which I can just call with, maybe I'll put GPE. Well, actually a common way to express potential energies is with a U, so I think I'll just use that. So UG is the gravitational potential energy. Then there's the elastic potential energy, which I'll call as UE. And I will define all of these. We also have kinetic energy. Kinetic energy is the energy due to motion of a body. So like a car that's moving, or a person running, or a squirrel climbing up a tree, they all have kinetic energy. And then there's more types of energy. Actually, this list can go on. I'm just going to bring out the most important ones. There's also something called internal energy, which I won't really represent. Maybe I'll just call it U internal. Yeah, that looks good. U internal has to do with bonds, molecular bonds, that energy that's stored in them. Also, you can think of it as the energy that's stored between protons and electrons or in the nucleus itself. So U internal is more, it feels like chemistry, I would say. It's something that we would calculate in chemistry more than in physics, but they both are important. Also, another part of internal energy has to do with temperature. So if you have water that's hot versus water that's cold, which one has more energy? Well, the water that's hot has higher internal energy, even if they both aren't moving or, they don't have any potential energy, so as to speak. They might differ because of the energies might differ because of the internal energy. All right. So I guess internal energy, you can think of it as molecules. You can think of it as temperature, anything with bonds. The structure of the material has to do with internal energy. All right. Let's define each of these energies. So I already defined internal, so I will now spend time on gravitational potential energy. So remember, how did we define work earlier? Work is equal to force dotted with distance, something like that, right? Well, you can also define energy with a similar definition. And let's talk about gravitational potential energy. So what's the force in gravitational potential energy? Well, if it's on Earth, we can define the force to be mg, remember? So m times the acceleration due to gravity, which is g. I'll put a little arrow on the g, dotted with the distance that the object moves. Now, mg only acts vertically, right? So if you want to climb up a hill or something, it's more hard than just going the same distance horizontally. Because what are you doing when you're climbing up a mountain? You're going against the gravitational force of the Earth pulling you down. So that gives you potential energy. So technically, d, displacement, is a height. So that's why what we do is we write it as mgh, so that we remember that it's the height and not the horizontal distance, it's only the vertical distance. And that's why that g dotted with d disappears, because g is in the vertical direction. And since it's in the vertical direction, when I dotted with d, the distance that you travel, only the height component will be taken. So even if you travel some sort of a distance that looks like this, a displacement that looks like this, we will only take the h part of it. We will eliminate whatever else this is. We'll just get rid of it. We won't use that when we're calculating potential energy. All right, so I hope that makes sense. So this is how potential energy is defined. Some textbooks like to put a negative sign over here. That's really your call. I don't like to use negatives. It just confuses everything. So I won't be using a negative sign. Okay, and if you want to calculate the change in potential energy by putting a delta, you can write it as m doesn't change, g doesn't change, the h is what's really changing. So that difference in height tells you the difference in the potential energy. So this is kind of like the total potential energy. Let's say you're above sea level by 30 meters, then this would be, your h would be 30. But if you want to calculate what's the difference in my potential energy, or how much potential energy did I gain when I moved from, let's say, 20 meters to 30 meters, then you would have to do 30 minus 20 right over here for h, okay? So I hope that makes sense what the difference between just potential energy and change in potential energy is. All right? Moving on, let's talk about elastic potential energy. To talk about elastic potential energy, we have to talk about Hooke's law. So Hooke's law says that the applied force on a spring or on something that's, stretchy, like a band or something, is directly proportional to the extension. And this is only within the elastic limit. So if you have a spring and, you put a weight on it, the amount by which the spring extends is directly proportional to the force. So let's say the spring was initially, at this height. And then after putting that little weight, it went down by height h. So what it's saying is whatever force this is applying, this weight is applying, that force is directly proportional to the extension, which, I called it h. Let's call it x, all right? That's the the popular variable for extension. So we're going to call that x. So I can write F is equal to Kx. All right, where K is the elastic limit. By the way, this proportionality is only within the elastic limit. If you ever played with springs before, remember the springs that go down the stairs? And yeah, I'm pretty sure a lot of you have pulled them to their limit and they don't go back to their original shape after that. They become deformed. So this law, Hooke's law, only applies if you don't deform your spring by pulling on it too hard. So you have to stay within the elastic limit. The moment you go beyond the elastic limit, don't expect Hooke's law to apply anymore. So that's Hooke's law. Now we're going to derive the elastic potential energy. Now remember, I used this definition for work earlier, right? Well, actually a more correct definition for work is the integral. So I'm sorry for bringing calculus in all of a sudden, but it really can be helped. So it's F dotted with actually a small component of displacement over the entire displacement, but you can approximately say that this is true if things aren't changing in certain ways. I know I'm being very vague over here, but I really don't want to get too much into the math because it's not really required. Most exams and stuff will either expect you to memorize the formula or they give you a formula sheet. They don't expect you to know how to derive it. So I will not be going through the math. But for our potential energy, elastic potential energy case, this F is Kx, and it becomes dotted with this dx, and x and dx are in the same direction, so I can just write it as kx with dx. And if you know a thing or two about integration, this becomes 1/2 kx squared. All right, if you don't know much about calculus, then don't worry about it. Maybe look it up if you're interested, but that's our elastic potential energy. So it's 1/2 the constant, we call it, does it have a name? Well, I just call it the extension constant or whatever, or the elastic constant, and times the square of how much the spring or whatever object you're studying got extended by, all right, or got compressed by as well. Compression and extension are equivalent in terms of potential energy. The force direction will be different, but in terms of elastic potential energy, they'll store the same amount, because we don't care about directions when it comes to energy. All right, so that's the potential. That's it for potential energies. Now we're going to talk about kinetic energy. So kinetic energy, you might already know the formula 1/2 mv squared, but I'm going to try deriving it using calculus. And I'm sorry for those of you who don't like calculus, but I want to show you that these come from somewhere. It's not just imagination or something. They do come from somewhere. So work is F dotted with dx. Right? And for kinetic energy, it's the energy of motion, right? It's the energy associated with motion. So if you remember Newton's second law, that's F is equal to ma. So we will put ma over here, ma dotted with dx. Now, if you know a thing or two about calculus, you can't integrate over two different variables. A needs to be in the form of x. And to do that, I'm going to do a little bit of fun stuff here. So I know A is dv dt, and for those of you who I didn't define it as dv dt, remember I said A was equal to delta V over delta T, and you can actually say that delta becomes very small and it becomes dv dt. Okay, and that's the beauty of calculus. I'm not going to get too much into this. All right, and you still have your dx here. All right, so what's going on over here? So I'm going to assume, by the way, over here that the acceleration is in the same direction as the x. So I can approximately just, get rid of this. So, and I guess in principle, I'll get rid of the signs then, the vectors. So now I can write this as mdv and move the dt below the dx. Well, dx dt is what? Delta x over delta t, which is just the velocity. So it's mv, I just moved this here and then said it's v, so it's mv dv. And now if you know a thing or two about calculus, is 1/2 mv squared, which kind of looks similar to the elastic potential energy 1/2 kx squared. They do follow similar rules. So this is the kinetic energy, all right? And if you don't know what this means or how to think about integration, the way I think about integration is as area under the graph. So if you're trying to wrap your mind about where did this even come from, this just means the area under, let's say this is F and this is X. How do I erase it? Okay. Let's say that's F and that's X, and this is the graph. Well, this just means the area under this graph. All right? That's all it means. And that's what we're doing over here. We're actually calculating the area under this graph without drawing a graph and actually calculating the area. It's just a handy tool to do it. All right, so that's how we get the kinetic energy. Now that we know how to derive different energies, even if we can't derive it, we know what they are. We know what potential energy, gravitational potential energy is, it's mgh. We know what elastic potential energy is, that's 1/2 kx squared. And we now know what kinetic energy is, it's 1/2 mv squared. So we have all these formulas, and now we can always say that the total energy is equal to the sum of all these energies. So it's Ug plus Ue plus Ke plus the internal energy and any other energies that are there, okay? These aren't the only energies that exist, of course. But for our purposes, let's say that these are the only energies that exist, all right? That's what energy is. Work is the change in energy. So it would be the change in each of these energies. So I would say the change in, the potential, the change in the elastic potential, the change in the kinetic. So you're doing final minus initial for each of them, plus the change in the internal and any other quantities. All right, so that's what work means. So I hope you understand the difference between work and energy. All right, and this is called the work energy principle. It has a fancy name, work. I'll just put work -E principle. All right, I don't really like writing a lot. Some people call it the work energy theorem. And this is actually important because it opens up a discussion on a device that someone has never built, but a lot of scientists, they really think about this a lot. It's called a perpetual motion device. And what this really is it's a fictitious device that's able to produce work continuously without reducing the energy of the system. But by the work energy principle, we know that this can't be the case. Whenever we have work, some change in energy is going to happen. So this can't exist, but there have been a lot, there has been a lot of work done in trying to find a perpetual motion device, or trying to create one, at least theoretically. And it's interesting because if one is able to make a perpetual motion device, then our whole concept of energy goes down the drain. But for now, no one has, so work energy principle is safe for the time being. Okay, so now we're going to talk about conservative forces. And it's going to make a loop back to what we've been discussing. All right, so now we're going to talk about an interesting concept. It's called conservative forces. So what is a conservative force? Well, it's a force where the work done for this force in a round trip is equal to 0. So it has to directly do with work. Let's go through an example to understand this. So let's say there's a little ball and it's lifted up. So we lift it up. Okay, so now it's up, all right? What is the work done to lift the ball up? Well, the work done to lift the ball up is simply equal to the change in the potential energy, right? Is there any other energies here? Not really. There's no elastic, there's no kinetic, because we're just taking it from the bottom and putting it up. And the motion, both are at rest. So here it's at rest, and then when it comes up here, it's at rest. So we don't even have to consider kinetic energy. And the internal energy, there's no temperature or anything really changing. So there's only potential energy. So there's a change in potential energy. So it starts off at a height of 0, let's say, and goes up to a height of h. All right. So when we write this down, it's going to be Ug final minus Ug initial, because we have a delta. Ug final is mgh final minus mgh initial. What is the final height? It's just h. So let's write down h. What is the initial height? The initial height is just 0. So we can just say, oh, this is a 0 term. So this is the work done to lift the ball up. So I'll put an L next to it, meaning the work done to lift the ball. What about leaving the ball back down? So we're doing work in a round trip, right? We put the ball up, and we need to bring the ball down. So that's the ball. So it started at height h, and now it's going to come down. Okay? So the work done, in that case, is still UG. All right, and we have to go through the same process. mg final, mgh final minus mgh initial. But now this is the aha moment. So what is h final in this case? H final, it started off here and it ended up here. So the final h is 0. So this term goes to 0. What about initial? Initial is 10. The negative sign is here, so it's negative mgh. Did I say h is 10? H is just h, okay? H initial is just h. It's not 10. All right. So this is the work done to bring the ball down. So I'll just put a D next to it. So the work done in a round trip, the process of bringing that ball up and then bringing it down is 0. And you might think this is obvious and why am I making such a big deal about it? Because you'll see another example where forces don't do this. All right, the work done in a round trip due to a certain force won't be 0. But in this case, I take WL, add it to WD. So you can say the work done in a round trip is WL plus WD, and that's WL was mgh and WD was minus mgh, and these two cancel out and we get 0. So what was the force over here? It was the gravitational force. Fg is a conservative force. All right, this is a conservative force. The elastic force as well, which I'll call as Fe, is also conservative. All right, for kinetic energy, it's not, what's the force for it's MA. You can say that's also that work, that's whatever force it's associated with it, it's conservative. Okay, so that's that. All right, that's a conservative force. Now there's the opposite, where you have a non-conservative force. This is where when you do work in a round trip, for that particular force, it doesn't go down to 0. Let's take an example of this. Let's say you have a whole carton of stuff you have to shift to another location in a store because your manager said so. So you start off here. Let's say this is your initial position, and you end up here. This is where you have to take this big load of stuff. So you put a lot of effort in and you finally move it here. Okay? And when you did this, there was some friction force that was acting opposite to you moving the box. So for simplicity, let me call x final minus x initial as just x, all right? That'll make our lives easier. And the friction force, so one moment. When I move from x initial to x final, this is the direction that we're moving in. And the friction force is obviously going to be in the opposite direction because it's opposing the motion. So let me draw a red arrow for friction, and I'll put friction up here. So that's the force due to friction. And I will call this force as just plain old F. All right, that's the friction force. So the work done in moving the box from this position A to B, we'll call this as A, maybe B. So from A to B is equal to F dotted with dx. And in this case, they're in opposite direction, so it's just minus fx, right? So that's the work done to move it from A to B. Now let's say your manager sees what you've done and he's like, well, you completely misunderstood what I said. I didn't want you to move it over there. And you roll your eyes and you're like, fine, let me put it back. So now you move the box in the opposite direction. So now you had to move the box from B to A. So let's talk about that. So the W from B to A is again F dotted with dx. So we're moving in this now towards the left, right? And the friction will always be in the opposite direction of motion. So now the friction moves towards the right. So the force of friction will be in this direction, towards the right. So again, Fx will be negative because we do dot product between the two of them. By the way, I know I wrote F dotted with dx, and that might have confused you. I meant to say F dotted with x. I'm still thinking about calculus, but then not being complete. So please forgive me. It's f dotted with x, okay? Or f dotted with d if you like. X, d, these just represent distances, all right? They're just variables, you can change them. So again, it's going to be negative fx. So what is the work done in a round trip? The work done in a round trip is moving it from A to B, and then back to B, from B to A, right? That's the work done in a round trip. The box went back to where it started from. And this is minus fx plus minus fx, which is minus 2fx. It does not cancel out. And if you are surprised, take a look at the calculations once again, and it really makes sense. So the force of friction is a non-conservative force. Friction is non-conservative. I'm just going to write NC for non-conservative forces. All right? So that's interesting. There are other examples of non-conservative forces, things like air resistance. That's also a non-conservative force. Mostly, you can think of non-conservative forces as imperfections. When we usually do physics calculations, we try to ignore the imperfections like friction, air resistance. So these are non-conservative forces. They make calculations more complicated. All right, so now let's go back to our fun old isolated system. If you remember, what is an isolated system? Come on, quiz time. If you don't get this right, get a 0 on the test. Okay. An isolated system is one where the sum of external forces is 0 and no mass can come in. So mass can't come in, all right? Whatever stays in can't go out and nothing new can come in. That's an isolated system. So what is the work done due to an isolated system? Remember, what is the definition of work done? Work done is defined as F dotted with D. But if this is 0, then the work done is 0. If the work was equal to delta E, that means delta E is 0. In other words, that means E is going to be conserved. So this is called, does this have a law? I don't think it has a law. Well, for an isolated system, we say energy is conserved. And we really mean the mechanical energy, all right? So what is mechanical energy? I know I didn't define this. Mechanical energy is the total energy caused due to the conservative forces. So like potential energy, kinetic energy, all of those those energies caused by conservative forces, that's mechanical energy. Friction is not part of that, all right? Let's say we have a non-conservative force involved. Let's say, some non-conservative force comes into the picture. If we do have non-conservative forces, oh, by the way, just a heads up, this is an isolated system, plus there are no non-conservative forces. I forgot to mention it. Then only this idea applies, all right? Otherwise, this isn't true. So there are no non-conservative forces. Then this is true. Then E is conserved. But if we do have a non-conservative force, then we can't say that delta E is equal to 0. That's not true anymore. So this is not true. The change in energy is actually equal to the work done due to non-conservative forces. All right? So that's that. So this is important. And this is actually going to help you a lot, this equation. In fact, I would say that this equation in many ways is equivalent to this equation that we had earlier. The difference between these two equations is energies, these are scalars, and the force and acceleration, these are vectors. Which one do you think is easier to solve for a certain value like height or velocity? Well, actually, this one's easier. I'm more familiar with using Newton's second law because that's what's been stressed on a lot. But when you have to deal with directions, signs, it gets very confusing. The preferred way to calculate and solve equations, like solve for variables and whatnot, is to actually use this equation up here. So when I go through the problems for this chapter, I'm going to try both approaches and show you how the calculations unfold. And then you can be the judge to decide whether you like the energy way of solving things or the force way of solving things. It's quite interesting to solve the same problem in different ways and get the same answer. It just shows how intricately linked all these ideas are, because this whole idea of energy we derived it from the idea of force. So this is a very natural, this equation is actually the same idea as Newton's second law. All right, to wrap things up, I want to talk about one last idea, or maybe two last ideas, no, just one. One last idea and we'll be done for the day. So now we talked about the rate of changes of things all the time, so we might as well talk about the rate of change of energy. And this might be relevant to your electricity bill if you've ever seen your electricity bill. So the rate of change of energy over time, so you can think of it as delta E over delta T, is called power. And yes, if you've seen your electricity bill, it's in kilowatt hours, right? Kilowatt hours. So this is joule over time, and this quantity is called a watt. So power is kind of like how much energy is like changing over a certain amount of time. It kind of tells you the rate of things, like a generator might say, or a light bulb. So all these quantities in electricity especially, they use the concept of power quite a bit. Horsepowers, if you remember that too. So just having a large amount of energy sometimes isn't enough. You want to know the rate at which you can produce this energy. And that's where power really comes in. All right? So that's pretty much it for today. I wanted to talk about escape speed as well. Might as well talk about it. Escape speed. So I'll just discuss it here since it's a relevant topic. What is escape speed? So let's say we have the Earth, right? That's a very small Earth. Let's draw a bigger Earth. So let's say this is the Earth, all right? And there's an object going around it, like a satellite or something, and it's just going around the Earth, no issues. What if this object wants to escape the Earth? With what speed does it have to move? This is a very common question, and that's why I want to address it here. So how fast would this object, let's call it S, have to move for it to escape Earth's gravitational pull and just go out into the unknown, right? This is called the escape velocity, by the way, this velocity that it needs to escape the Earth. And usually they ask what is the minimum velocity that it needs. Because you could give any crazy number. You can say 10 to the power 9 meters per second, right? Or infinite speed. But they asked them, people have become smarter. So now they asked what's the minimum velocity that it needs in order to escape the Earth's gravitational pull. So what is S's escape velocity? And that we can use energy to solve this problem. That's the beauty of it. So the idea is that the Earth is bounding this object or binding this object S by the gravitational potential energy. So that's UG. So we need to exactly match that energy in order to escape. S needs to match that energy, and it needs to match it in speed. Speed, when you think about speed, that's automatically kinetic energy. So that's the equation you come up with. Now, you might be tempted to write UG as MGH, but don't do that. It's because this object is now further away from the Earth. You can only use MGH when the object is very close to the Earth. Because if you remember, this is an approximation of the general law, but I can't now use this approximation anymore, so I'm going to use the general law. So that's GME, and let's say for S, it's just M divided by the distance between the Earth and this object, which I'll just call as R. So that's R squared. So this is the force, so I have to still multiply by a distance, which is just R once again. All right, that's the gravitational. So this is the force times the distance is equal to 1/2 mv squared. I used m, the little m, not the big M, because we're talking about the speed of S, not of E. E isn't the one that's escaping, S is escaping. All right, so this R and this R cancel out, and we're solving for V, so this M and this M actually cancel out as well, and we're left with 2gme divided by R, and the square root of that is equal to V. So that is your velocity. This is called the escape velocity, and you can apply it to any situation. So this was for Earth. You could apply it for the sun. How much velocity does the Earth have to move to escape the sun? Then this R and this ME value would change, of course. But yeah, that's pretty much it. It doesn't depend. Notice that this equation doesn't depend on the mass of the object that's escaping. So it doesn't depend on the mass of S. It only depends on the mass of the other object and the distance between the two of them. That's an interesting thing to note. And this has to do with black holes as well. Why are black holes dark? It has to do with escape velocity. Anyhow, I'm going to leave this lesson with that before I start rambling about black holes. I'll see you next time for extended bodies at rest. Yeah, that sounds really weird, but thank you for watching.